So this is linear algebra, lecture 6. And linear algebra studies vector spaces and linear transformations. So a linear transformation is a function. So suppose we have that V and W be vector spaces. Over the field F, which could be the real numbers or the complex numbers. And so a function T from V to W is called a linear transformation. If it satisfies the following two properties. First, T of V plus V prime is T of V plus T of V prime, and T of C times V is C times T of V for all vectors, V and V prime in the vector space V, and all scalars C in the field F. So a basic example would be if we take F to be the real numbers, V to be the n-dimensional vector space Rn, W to be the m-dimensional vector space Rm. If we let A be an m by n matrix, we define a function T sub A from V to W by matrix multiplication. It is multiplication of a matrix and a vector. T sub A of the vector V is the matrix A times V. So if this is the matrix A1 up to A1n, AM1 up to AMN, and V has coordinates x1 to xn, this is just the usual matrix multiplication. So the first coordinate is summation A1j xj, j goes from 1 up to n, down to the nth coordinate, summation j goes from 1 up to m, amj xj. We'll spend a lot of time on linear transformations, but there's a bit more that I have to do about vector spaces. And I want to review what I did yesterday, which is, in some sense, the most important theorem in linear algebra, which is explaining that there is a well-defined number called the dimension of vector space. So let me start by reviewing this. And when we were studying systems of linear equations, we had the following theorem. So this is a theorem that we proved in the chapter on systems of linear equations. Suppose we have a homogeneous system of m equations in n variables, a11x1, a12x2, up to a1 and xn equals 0. n variables, and homogeneous means the right-hand side is 0, and m equations, so the last equation is the mth. So a homogeneous system of m equations, and any homogeneous system has a trivial solution where all the x's are 0. So if the number of equations is less than the number of variables, if n is bigger than m, then the system has a non-trivial or non-zero, they mean the same thing, solution, a solution x1 up to xn in Rn with not all the x's equal to 0, with xi different from 0 for at least one coordinate xi. So this is a big theorem about systems of homogeneous linear equations. More variables than equations means there's always a non-trivial solution. And this is the key to proving that vector spaces have dimension. So let's go back now to a vector space. So V is a vector space over the field F. And I write F instead of R to emphasize the fact that we have vector spaces over all fields. We don't have to consider just the real numbers, though that is the basic case. Second basic case is the complex numbers. We have vector space over the field F, given vectors V1 up to Vk in the vector space V, and scalars C1 up to Ck in the field F. We have what is defined as a linear combination of the vectors. You take the vector v1 multiplied by c1, the vector v2 multiplied by the scalar c2, and so forth, ck times the vector vk, and add these up. So this is called a linear combination of the vectors. And we say that v1 up to vk is sequence of vectors. Is linearly dependent if there exist scalars, not all 0, some can be 0, such that this linear combination is equal to the 0 vector. And the sequence of vectors is linearly independent otherwise. So another way of saying that is if whenever C1, V1, C2, V2, up to CK, VK is equal to 0, this happens if and only if all of the scalars are equal to 0. So if you have a sequence of vectors V1 up to VK, they're said to be linearly dependent if their scalar is not all 0, for which the linear combination is the 0 vector, and linearly independent if the only linear combination of the vectors that gives you the 0 vector is the trivial linear combination with every coefficient is 0. So these are two fundamental definitions that you have to think about a lot. So for example, typical question, are the vectors 2, 3, and 5 minus 1 in R2 linearly dependent or independent. So we have to know what are the solutions of C1 times the first vector plus C2 times the second vector equal to the 0 vector. What numbers C1 and C2 satisfy this vector equation? Let me write x and y instead of C1 and C2. What are the x's and y's such that x times 2, 3 plus y times 5 minus 1 equals 0? So this is the same as, see, if you take x times 2, 3 plus y times 5 minus 1, x times the first vector is 2x, 3x, and y times the second vector is 5y minus y. And when you add them, you get 2x plus 5y, 3x minus y. And you want to know for what x and y's is this the 0 vector. So this is the same as solving two linear equations and two unknowns. 2x plus 2y equals 0. 3x minus y equals 0. And if you solve these equations, you'll see there's only one solution. X and y is 0. So therefore, the vectors 2, 3, and 5 minus 1 are linearly independent. Suppose we have S, a subset of a vector space V, and let W, I'll write S with brackets around it, be the set of all linear combinations of vectors in S. So W is the set consisting of everything of all linear combinations, summation x sub I, s sub I goes from 1 up to k, where s1 up to sk are vectors in S, and x1 up to xk are scalars. They're in the field F. So all possible linear combinations of vectors in S. So here we have our vector space V. Here we have the set S, and we look at all linear combinations of vectors in S. So in particular, S is contained in W because the vector S is in S. 1 times S, which is S, is in W. So W contains S, but it's bigger. It contains sums of vectors in S. Infinitely many, because you have infinitely many numbers in your field. You have an infinite field. And we have a little theorem or lemma that says W is a subspace of V. So first, if we take the linear combination, if S is in S, 0 times S is in W, and 0 times any vector is the 0 vector. So W certainly contains the 0 vector. And if summation xi, si is in S, and summation yi, si is in S, then if you add them, you get a summation xi plus yi times s sub I. Sorry, it's in W. is in W, and C times summation xi si is summation cxi si, just by distributivity, is in W. So this set W contains the zero vector. It's closed under vector addition, it's closed under scalar multiplication, so it's a subspace. And if W is a subspace of V, then we say that S generates W if the subspace, the set of all linear combinations of vectors in S equals W. So that's our short limitation. And we say that, so again, we have our vector space V, a subspace W. W could be all of V. V is a subspace of itself. But a basis, so this is the important word, a basis for a subspace W of V is a set V such that V generates W and V is linearly independent. What is the most important theorem about vector spaces says the following. Let me just emphasize one thing. So the subspace W of V is finitely generated if there is a finite set S that generates W. And the big theorem says that every finitely generated subspace W has a basis, finite basis. All bases have exactly the same number of elements. And what we call the dimension of W, that's the, is the number of vectors in a basis. So let's look at an example of this. We proved a few minutes ago that the set of vectors 2, 3, and 5 minus 1 are linearly independent. call this set B. I will show that B, in fact, generates the vector space R2. So what does that mean? That means that every vector is a linear combination of 2, 3, and 5 minus 1. So we have to must show that for all vectors, let's see, I don't know what to call them. Let's say AB. There exist scalars, numbers, x and y, such that x times 2, 3 plus y times 5 minus 1 equals AB. Let me call this B1 and B2. So the scalars x1 and x2, such that x1, 2, 3 plus x2, 5, 1 equals B1, B2. That is, to say that the set B generates R2 means that every vector in R2 is a linear combination of the two vectors in B. So for any vector B1, B2, I can solve this equation. B1, B2 is this linear combination. If we write this as one vector, this is 2x1 plus 5x2, 3x1 minus x2 equals B1, B2. So we have to solve this vector equation, which is the same as solving the following system of two equations and two unknowns. 2x1 plus 5x2 equal B1. 3x1 minus x2 equals B2. And this can be solved. So I'll leave it to you to check. This is solvable. So therefore, B, which is the vectors 2, 3, 5, minus 1, is a basis for R2. It's a nice example of a basis. There are many bases for R2. This is one. Okay. So how do we prove that every finitely generated subspace has a basis? And then to prove that every basis has the same number of elements. So let me prove it as I can do this. It can be done in many ways. So let's start with the lemma. Let S, consisting of S1 up to Sk, be a linearly independent subset of the vector space V, and let W be the subspace generated by S. So here's V, here's the set S, consisting of the vectors S1 up to Sk, and here is the subspace W that it generates. Suppose W is not all of V. That is, W is a proper subset of V. Let little v be any vector in V slash W. That means V is in V, the vector space V, and V is not in W. So in standard mathematical notation, this is V is in, this is a kind of a epsilon. V is in V, and V is not in W, which is the same as saying, again, this is just mathematical notation, V is in V slash W. In any case, here is W, and you have some vector V that's not in W. Then I claim the set S union V, which is S1, S2 up to S sub K and V, is a bigger linearly independent set. And the proof goes as follows. Suppose you have some linear combination, x1, s1 plus x2, s2 plus s sub k, v sub k, x sub k, s sub k plus yv is the zero vector. I want to show that this set of k plus 1 elements is linearly independent, which means I have to show that all the x's and y are zero. If y is zero in this equation, then x1, s1 up to xk, sk is zero, which means all of the x's are zero, because S is an independent set. That was our hypothesis. The set S is linearly independent. But if y is different from zero, then yv is minus x1, s1 minus x2, s2 minus xk, sk. If y is different from zero, I can divide by y. Y over y is 1. So v is this linear combination of the vectors s1 up to sk. So that means it's in W, which is the set of all linear combinations of vectors in S, and that's a contradiction. So y cannot be different from zero. Y has to equal zero, and if y equals zero, the x's are zero. So that's the proof of this very useful lemma. So recall, S is a finite set that generates W. Consider the set of all linearly independent subsets of S. So here you have the set S, and there are different subsets that are linearly independent. S is finite, so these are all finite sets, and so each of them has a size, and let S prime, or let's say let B be a maximal or largest linearly independent subset of S. I claim B is a basis for W. So here's our picture. Here's V. Here's S. And here's W, the subset generated by S. And sitting inside of S is a smaller set S prime, which is the largest linearly independent subset of S, or card B, the largest linearly independent subset of S. So the subspace generated by B is contained in W, because everything in B is a subset of S, so every linear combination of elements in B is a linear combination of elements in S, and so it's contained in W. If the subspace generated by B is not W, then then the subspace generated by B would be some proper subset of W, and there would be a vector V that's in W, but V is not in B. But by the lemma we just proved, B union V is linearly independent. It's a linearly independent subset of W. And the number of elements in B union V is the number of elements in B plus 1. I should be a little bit more careful about how I stated this, so let me just revise. Everything I wrote is correct, but I just have to add one more comment. So we have a vector space V, a set S, and a finite set, and W is, and the set S is a finite set that generates W, because we're told W is finally generated. There's some finite set of vectors that generates W. So you can look at all linearly independent subsets of S and choose the largest one. Let's call that B. And so B is a maximal linearly independent subset of S. And I claim that this B is a basis for W. That means that B generates S. So the subspace generated by B is contained in W. And if it's not equal to W, then, so really I want to say, put it like this. Let me start this on, let me do this on another page. So I have vector space V, subspace W. W is a finitely generated subspace of V. And finitely generated means there exists a finite set S that generates W. And let B be a maximal, largest, if you like, linearly independent subset of S, and let W prime be the subspace generated by B, which is contained in W. If S is not in W prime, for some vector S in the set S, then we have the following picture. Here's W prime, and we have a vector S. It's not in W prime. But then B union S is a linearly independent set of vectors, and it's a subset of S. And the cardinality of B union S is the cardinality of B plus 1, which is bigger than the cardinality of B. And that's impossible, because B was the largest linearly independent subset of S. So therefore, S is contained in W prime, the whole set S, which means the subspace generated by S is contained in W prime, and that's W, and W prime is contained in W. So W prime, which is the subspace generated by the set B, is the whole subspace W. And that's what we wanted to prove. B is a linearly independent subset of S that generates W. So I could restate what I just proved as follows. This is, let's say, a theorem. Let S be a finite subset of V, and let the subspace generated by S be called W, then S contains a basis for W. Okay. So now let's prove the big theorem. Let B and B prime be finite bases for the subspace W, then the cardinality of B is the cardinality of B prime. Remember that if I write X with absolute value signs around it, this means the number of elements in X, which is called the cardinality of X. So proof. Well, actually, the way I proved this yesterday was good, and I'll just do it again. So there's one sort of lemma or theorem that we need first. So we have, suppose we have that B and B prime be finite sets. In W, if B generates W, and B prime is linearly independent, then the number of elements in B prime is at most the number of elements in B. Let's see. What was the notation I used yesterday for that? Let me use exactly the notation I used yesterday. So in the notes, this is theorem 6. We have S consisting of M vectors. It's a finite subset of the vector space V. It's contained in V. And we let W be the subspace generated by S. Let V1 up to Vn be vectors in W if n is bigger than m. You have m vectors that generate the subspace and n other vectors in the subspace. If n is bigger than m, then the sequence of vectors v1 up to vn is linearly dependent. And the proof goes as follows. For all j from 1 up to n, the vector vj in this set is some linear combination of the w vectors. I goes from 1 up to m, aij, wi. Suppose we take a linear combination of the vectors vj. Suppose you look at summation xj vj. J goes from 1 up to n. This is summation, j goes from 1 up to n, xj, and vj is summation, I goes from 1 up to m, aij, wi. These are finite sums, and we can interchange the summation. Summation I goes from 1 up to n. Summation j goes from 1 up to, I goes from 1 to m, j goes from 1 up to n. I have aijxj, which is a scalar, times the vector w sub I. So the coefficients of the vectors w sub 1 up to w sub m are these. So, and so if this equals the 0 vector, sorry, put it differently. So let me look at these coefficients. So this coefficient, like when I is equal to 1, this is a11 x1 up to a1 and xn, and down to am1 x1 up to amn xn, and xn. These are the coefficients. And if I look at this system of homogeneous equations, I have m equations, n variables. If m is less than n, this means there's a non-trivial solution of these equations. So I can find scalars x1 up to xn, not all zero, such that summation xj vj is the zero vector. So m less than n implies the vectors v1 up to vn are linearly dependent. And so if they're independent, that can only happen if m is greater than or equal to n. Not necessarily, but if they're linearly independent, n is less than or equal to m. So now we can prove the big theorem. So we have V1 is a finite basis for W. V2 is a finite basis for W. Say the number of elements in V1 is equal to M1. The number of elements in V2 is equal to M2. So V1 generates W because it's a basis. V2 is linearly independent because it's a basis, which means the number of elements in V2 is less than or equal to the number of elements in V1. So M2 is less than or equal to M1. But symmetrically, V2 is a basis, so V2 also generates W, common. And V1 is a basis, so V1 is linearly independent. So the number of elements in V1 is at most the number of elements in V2. So M1 is less than or equal to M2. So if you use two numbers and each is less than or equal to the other, M1 equals M2. And this number, which is the number of elements in a basis, is called the dimension of the vector space. There's one other thing which is you would expect to happen, but have to prove that it does. Suppose you have a vector space V. You have a vector space W1 contained in a bigger vector space W2. So W1 contained in W2 contained in V. Then you expect the dimension of the smaller space to be less than or equal to the dimension of the larger space. And a quick proof of that is the following. Suppose you let dimension of W1 be K1, dimension of W2 be K2. So suppose you take a basis for the small space V1 with the cardinality of V1 equal to K1, and W2 has a basis V2 with the cardinality of V2 equal to K2. So W1 is V1 is the basis for the small space W1, is a linearly independent subset. It's linearly independent. It's a linearly independent subset of W1, also of W2. B2 is a basis for W2, so it generates W2. So the cardinality of B1 is less than or equal to the cardinality of B2, or K1 is less than or equal to K2. That's really all you need to say for the proof. So let's look at some of the exercises, just to get some sense of what this means. So this is section 1 of the chapter, exercise 1, part A. So we're looking at R2, that vector space. Suppose I take S1 to consist of the two vectors 1, 0 and 0, 2. So what is the subspace they generate? The subspace generated by S1 is all linear combinations of these two vectors. So this is the vector x0, and this is the vector 0, 2y, which is x, 2y. So the subspace generated by S1 is all vectors you can write in the form x2y, but this is, I claim this is all of R2. If I take any vector, b1, b2, I can write that as b1 2 times b1 over 2. So that's like the vector b1, 0 plus 0, 2, b1 over 2, which is the vector b1 times 1, 0 plus b2 plus b2 over 2 times the vector 0, 2. If I take the vector 1, 0 and the vector 0, 2, and I take this linear combination, I get b1, b2 for any b1 and b2. So the subspace these two vectors generate is the entire space R2. And I claim these vectors are linearly independent. If x times 1, 0 plus y times 0, 2 is 0, 0, that's the same as saying x 2y is 0, 0, which is the same as saying x equals 0, 2y equals 0, which is the same as saying x equals 0 and y equals 0. So that's a proof that these two vectors are linearly independent. Let's look at 1b. Here, S2 is the set of vectors 1, 1, and 1 minus 1. So let's see if these vectors are linearly independent or linearly dependent. Suppose x times 1, 1 plus y times 1 minus 1 is the 0 vector. So it's the x times 1, 1 is the vector xx, and y times 1 minus 1 is the vector y minus y. So that's x plus y, x minus y. And that's equal to the 0 vector if and only if x plus y is 0 and x minus y is 0. But if you add these two equations, you get 2x equals 0. So x is 0, so y is 0, if and only if x equals y equals 0. So therefore, S2 is a linearly independent set of vectors. The only linear combination of these vectors, which is 0, is when you take the trivial linear combination, x and y are 0. Now, what do they generate? Well, I claim the subspace generated by S2 is all of R2. In other words, I claim that for any x and for any b1, b2, for any vector, x1, 1 plus y, 1 minus 1 equals b1, b2 is solvable. That's the same as saying x plus y, x minus y equals b1, b2 has a solution. That's the same as saying you can solve the equation x plus y equal b1, x minus y equal b2. And of course, it's easy to solve these equations. Again, if you add, you get 2x is b1 plus b2. So x is b1 plus b2 over 2. If you subtract, you get 2y is b1 minus b2. So y is b1 minus b2 over 2. So for these values of x and y, you represent this vector as a linear combination of 1, 1, and 1 minus 1. So this set S2 is also a basis for R2. Suppose that B, say V1 up to Vn, is a basis for vector space V. So if I take any vector V in V, I can write V uniquely as some linear combination of the basis vectors. And these x's are unique, and I can define the coordinate vector of V with respect to the basis B. It's x1, it's this n-dimensional vector x1 up to xn, and I put a subscript B there to indicate this is the coordinate vector with respect to the basis B. Right, this is, sorry. So let me use this notation. For the vector V, the coordinate vector with respect to basis B is x1, x2 down to xn. So in the example I just looked at, I have R2 as a basis B, where the first vector in it is 1, 1, and the second vector in it is 1 minus 1. And if I take, for example, the vector V equal to 7 minus 5, I can write this as 1, 1 plus 6, 1 minus 1. And if you check, this is 7 minus 5. So that's 1 times v1 plus 6 times v2. So with respect to this basis, the coordinate vector for v is 1, 6. So the coordinate vector for the vector 7 minus 5 with respect to this basis is 1, 6. If I took a different basis, the standard basis, consisting of the vector e1 equal to 1, 0 and e2 equal to 0, 1, the coordinate vector for v, in this case, 7 minus 5 is 7, 0 plus 0 minus 5. That's 7 times 1, 0 plus minus 5, or minus 5 times 0, 1. So the coordinate vector for v would be, with respect to the standard basis e, would be 7 minus 5. So the important point here is that whenever you have a basis, you can represent every vector uniquely as a linear combination of the vectors in that basis. And you can write down the coordinate vector of your vector with respect to that basis. So what is an interesting problem in linear algebra is the following. So again, whenever you have a basis, you can represent every vector as a linear combination of the vectors in the basis in a unique way. So every vector v is x1, v1, x2, v2 plus ... up to xn, vn. And the sequence of x's, this is an n-dimensional vector, is called the coordinate vector of v with respect to the basis. If you change the basis, you get a different coordinate vector. And it's a natural question to ask, how does the coordinate vector change when you change the basis? So suppose we have a vector space v, and the dimension of v is equal to n. We have a basis. Let's say we have a basis script f consisting of n vectors, f1, f2, up to f sub n. So every vector v can be written uniquely as some summation xi, fi. I goes from 1 up to n. And the coordinate vector for v with respect to the basis f is x1, x2, down to xn. Suppose we have another basis, g. So it has to have n vectors, g1 up to gn. Any vector v is some linear combination, say summation yi, g sub I goes from 1 up to n. And the coordinate vector of v with respect to g is y1, y2, down to y sub n. And we'll prove that there exists a square matrix, an n by n matrix P, such that the coordinate vector of v with respect to g is the matrix P times the coordinate vector of V with respect to F. And this is called the change of basis matrix. So there's the following change of basis identity. So let's recall again, F is a basis with vectors F1 up to Fn. G is another basis with vectors G1 up to Gn. And these are both bases for V. So every vector is a linear combination of the vectors in F and also a linear combination of the vectors in G. So for all J from 1 up to N, the vector G sub J is some linear combination, I goes from 1 up to N, P sub ij, F sub I. Every vector in G can be written uniquely as a linear combination of the vectors in F. And let's just try to continue and do a calculation. Suppose we have a vector V, which is some linear combination y sub j, g sub j, j goes from 1 up to n. So the coordinate vector for V with respect to the basis G is y1, y2 down to y sub n. But this is summation, j goes from 1 up to n, y sub j, and gj is summation I goes from 1 up to n, pij f sub I. If I interchange summations, this is summation I goes from 1 up to n, summation j goes from 1 up to n, pij yj f sub I. But this is V expressed as a linear combination of fi's. So this is, let me write this as summation I goes from 1 up to n, x sub I, f sub I. So the coordinate vector of V with respect to F is x1 up to xn. But each xi is summation pij yj. J goes from 1 up to n. This is exactly what you get if you see, suppose I take the matrix P, which is P11, P12 up to P1n, in general PI1, PI2 up to PIN, PN1, PN2 up to PNN. I use these P's as the coordinates of a matrix. If I take P times the vector y1, y2 down to y sub n, the ith coordinate is summation pij yj. So this is exactly the matrix P. Well, it's the ith coordinate of the matrix P. So x1 to xn is exactly what I get by taking P times the matrix y1 up to yn. Or another way of saying that is, for this matrix P, the coordinate vector for V with respect to F is P times the coordinate vector of V with respect to G. All right, well, I think I will spend all day tomorrow explaining this again and doing examples, because this change of basis matrix is a tad complicated, and you have to do a number of examples, and they all take time to work it out. What we're doing is in section 4 of this chapter on vector spaces and linear transformations. So, but this is now core linear algebra. A finally generated vector space has a basis. The basis is a set of vectors that's linearly independent and spans the vector space. The theorem about dimension says that every vector space has a uniquely defined dimension. Some are one-dimensional, some are two-dimensional, some are 17-dimensional. Once you pick a basis, you can write every vector as a linear combination of the elements in that basis that defines the coordinate vector. And as you change the basis, the coordinate vector changes. But to get from one coordinate vector with respect to a basis to another coordinate vector with respect to a different basis, you can calculate one matrix that does the transformation, this change of basis matrix. And that's what we're in the process of talking about. So I'll continue with that tomorrow. Any questions?
No, Professor.
Okay. All right. Bye.
Take care. Have a great class today.